The title of the talk is about what the brain networks tell us about how an individual is experiencing tinnitus. So it's a fairly broad topic. We won't have the opportunity to delve it in detail, but certainly we can begin the conversation about it. So to set the stage for it, first I wanted to define what is tinnitus? So tinnitus is the conscious perception of sound in the absence of an external source. And when we talk about it, we consider both the sound itself, which is a percept, and the reaction to the sound. So when we are thinking about the sound itself, we think about the type of sound we are hearing, whether it's narrowband or more broadband sounds. We, in the clinic or in the lab, we can measure its pitch, loudness, duration since onset, the laterality, as in which side of the head, so to speak, it's more localized to, whether it's amenable to masking. Some of the sounds like crickets, as we say in the United States, are more amenable to masking than other sounds sometimes. When we think of the reaction, it's the psychological impact having chronic continuous tinnitus may have on the individual. Some of the common complaints we get are about sleep disturbances, concentration challenges, communication difficulties above and beyond the accompanying hearing loss, about distress, anxiety, depression, which seem to occur at higher levels in our tinnitus population compared to the general population. And in very rare cases, we also encounter suicidal ideation. Typically, if tinnitus is occurring comorbid with other conditions such as post-traumatic stress disorder. So the premise of my talk is to use brain imaging to complement our assessment of severity. So how do we go about assessing severity? When we've just listed the dimensions along which there is an impact on the individual. So this is hearing, attention, emotion, and often at rest or when we are at quiet, we hear our tinnitus to be louder. The gold standard continues to be self-report questionnaires, but again, brain imaging helps explain what is being reported in these questionnaires and sort of describe what is happening in the brain that leads to this kind of complaints. So very quickly, I wanted to put to you the sort of an idea of what these questionnaires are measuring. So we have a very popular tinnitus handicap inventory questionnaire going back in the mid-1990s and almost 30 years ago now. And it typically measured along 3 dimensions of function, emotion, and whether individuals are catastrophizing, having tinnitus. The more recent ones, about like 12 years ago, from Mary Mickle, was about the tinnitus functional index. And here you're measuring around 8 dimensions, how tinnitus impacts the individual, right? Again, it's intrusiveness, sense of control. So we are sort of developing the impact along multiple axes, essentially. So, this slide is conveying to you, I hope, the fact that there is quite a lot of differences between the questionnaires that we routinely use. So they differ on the number of items. They differ along how individuals are asked to respond. For instance, in tinnitus handicap inventory, we tend to have 3 levels, yes, sometimes, and no. But in other questionnaires, we can have something like 0 to 100. How strongly do you feel about something, right? And that's very different. So as researchers, as clinicians, we can come up with, these are all validated, by the way. So these are all validated questionnaires, but we find that no single questionnaire covers every dimension. Each questionnaire, because of time, typically time constraints, omitted some dimensions or some questions. The questionnaire is different in regard to item format, scaling, and wording. Sometimes it becomes difficult to compare treatment effects obtained in different clinics, but there exists strong correlation among questionnaires. Currently, we have no reliable psychoacoustic test for tinnitus. By this, I mean loudness and pitch matching that is indicative of the extent of the bothersome symptoms, and it is not also has diagnostic value. So what we are trying to all agree, though, despite this, that there is consensus about that the spectrum of symptoms that we find among the patients, right? So some report they're very habituated to the tinnitus, they're very much on the mild end. Others report extremely bothersome symptoms, so that we would put them at the severe end of the spectrum or this range of impact on the individual. So what we want to do is use these neural neural correlates of severity, because there is consensus that the impact ranges from mild to bothersome. Everybody agrees on that. They may not agree on the actual questionnaire being used. So it allows us to use brain imaging to understand the neural correlates of the severity. We think brain imaging is more objective, and it complements the self-report. Okay. Just to bring it back to sort of, I have this, I just put the slide in, and what I wanted to convey here is that traditionally, like on the left side here of your screen, we have what is highlighted in blue are the putative or candidate sources of tinnitus generation. And these are typically obtained from animal studies. And we see that there are many candidates for where tinnitus may be generated. But what brain imaging allows us to also think is have this very holistic view or this global view of tinnitus, where we are looking at, let's say, attention regions, emotion processing regions, auditory regions, those regions which are implicated in audition, for instance, or sound processing, and think of that as a more global picture. So my work, my lab's work, tends to be on the right side of the screen. We are more interested in what happens when someone has had tinnitus for a while. What changes do we see in the brain? Okay, so brain imaging studies, why use it, right? So tinnitus is subjective. We don't know if someone has tinnitus unless they tell us that they have tinnitus. So brain imaging allows us to non-invasively provide information about neural mechanisms underlying both how tinnitus may have been generated, how it arose, as well as what allowed it to become chronic. We think it's an objective measure. This is a subjective disorder, and the population itself is extremely heterogeneous for a variety of reasons, not just because of severity of symptoms, about the extent of the comorbid hearing loss, about any other co-occurring conditions, and so on. It allows us to estimate effective interventions, and so we'll talk a little briefly about this going forward. We are beginning to look to it to provide information necessary to develop new therapies. So this has been done in other labs, and we are beginning to do it in our own lab as well. We have worked really hard to dissociate tinnitus from the impact of hearing loss. So you may be aware that about 90% of individuals with tinnitus also have some form of clinically significant hearing loss. But the opposite is not true. We will have about 50% of individuals with hearing loss who may not have tinnitus. So we find this dissociation, which is very interesting and important as we are thinking about understanding the neural mechanisms of tinnitus. Lately, we've also begun to understand what does it mean to have tinnitus. Can we develop a theoretical framework that allows us to understand globally the impact on the individual, see its overlap with other neuropsychiatric conditions, for instance, and still understand again how treatments work. So the items which are in red is ongoing work in the lab, but I won't have time to discuss that today. Okay, so this is our MRI scanner, so magnetic resonance imaging. A lot of us have undergone imaging via the MRI, whether if you have a knee problem or a back problem or whatever. So you're probably aware of this very noisy machine, which we take a lot of effort to mitigate the sound, to reduce the sound heard by the participant going in. And this is one of the scanners that we have used in the past. It's been upgraded, but this is what it looks like. You go in and we take pretty pictures of your brain as you're doing different tasks. So there have been considerable advances recently. We are beginning to develop consensus in the field about the impact on what is the gray matter. So the gray matter is where we are doing the most of the functioning. This is right where the neuronal cells are essentially. We have a lot of consensus now, which is that the impact on, because of tinnitus, is mitigated. The impact of having hearing loss on the brain is mitigated to some extent if you have co-occurring tinnitus. So this seems to be a consensus developing in the field. So I'm very hopeful in the next 5 to 10 years, we will really develop this piece of evidence and see what the impact is and put it to rest. White matter are the roads or connecting different regions of your brain. We see more of an impact of tinnitus on white matter than we actually see on gray matter. We have used blood flow measures. This is using arterial spin labeling, and we see that globally there is an impact of that on the brain as well. Neurotransmitter concentrations are important, and we have seen it in animal studies, and there have been about 5 to 10 studies now in humans, and seeing what changes in excitatory and inhibitory neurotransmitters because of the presence of chronic tinnitus, and also the presence of chronic hearing loss. This is early days yet on this kind of work, but again, I'm very hopeful about it. What we'll focus on today is resting state, functional magnetic resonance imaging, and I'll talk about it in greater detail going forward. Okay. So resting state functional connectivity is sometimes used interchangeably with resting state functional MRI, but this is the functional connectivity is an analytical technique. What typically happens is you go in the magnet, you see a plus sign on the screen. You can either close your eyes or open your eyes, and you just lie down there for like 10 minutes or 15 minutes and so on. What we try to collect from you, the data we collect are these spontaneous fluctuations in neuronal activity as measured by your MRI, essentially, right? And this is what this kind of activity looks like. So this is your brain, and there are about 3 regions that are picked up here. One is this red region, which is the temporoparietal junction. There is a primary motor course, time course here. Motor cortex time course. There is the inferior frontal gyrus and its time course. And you can see that this kind of spontaneous activity goes up and down with time. In this case, the time dimension is about 6 minutes. Here is the bold signal, which is what is being picked up by the fMRI. And you can see that things go up and down at the same time between the TPJ and IFG, so the correlation is higher, about 0.55, while the correlation coefficients for the other coupling is lower. So what we would say is that the TPJ and the IFG talk to each other more than the other regions. So even at rest, where you are given no explicit task to do, you are allowed to daydream, have your mind wander. This is what is happening. And what the advantage we have with using this kind of imaging and this kind of analysis, it allows us to see multiple neural networks at the same time. So in this case, we can see DAN here is a dorsal attention network. So this is, very active when you're attending to something. But it's sort of reduced when you're at rest, which is shown here by the blue color. And this is the auditory network. These are regions in the primary and secondary auditory areas, which are, again, talking to each other a lot. If you're processing sounds, like, for instance, you're processing my voice, and then they are sort of reduced when you're at rest. So this is probably standard networks we see in a lot of imaging. Everybody understands this. But what is new is what we call the default mode network, which is in orange here. And this has higher activity when we are at rest, but it gets suppressed when we are doing a goal-directed task. Like, if I ask you to do an arithmetic problem or a multiplication, then this would be suppressed, the DMN or the default mode network. So the fluctuations that we see that the nodes of a network talk to each other more than they will talk to if you're not part of the network, right? Think about the networks we have for airline travel around the world. Some are more connected and some are less connected regions. So to tell you a little bit more about the default mode network, and this is important in tinnitus, so I'm spending some time here. So the default mode network consists of this very good connection in the central part of the brain between the frontal parts here and the more posterior parts here. And they allow us to monitor the external environment. If a loud sound comes in or our name is spoken and we turn around, even though we may be talking to a friend. Excuse me. It's also important in self-reflective actions when we are thinking about the future, when we are thinking what someone else is thinking about us. So that's theory of mind. And then also memories we may have about what happened in our own lives. The default mode network is also important because it is anti-correlated with the activity in the attentional networks. So when we find that the activity in the attention network goes up, the default mode network is suppressed and vice versa. And this is important. It has been shown to be to index, let's say, aging. It is disrupted almost in all sorts of conditions outside of young, healthy individuals. So coming back to resting state and tinnitus. So you can imagine why this was extremely popular in tinnitus research going back now almost 14, 15 years. And one of the reasons is that individuals with chronic continuous tinnitus are hearing the sounds even without doing any task. And the control participants, right, who do not have tinnitus don't hear anything. So we can ask two questions, which is number one is if hearing the sound, internal sound, puts them in a different state because, you're hearing sounds versus controls who do not, or can we determine long-term alterations in the brain, specifically multiple neural networks at the same time? And is this a trait-like feature that we are detecting when we are doing this type of analysis? So I can give you the punchline. What it seems to be is that we're detecting the trait-level differences rather than state level. And we work this in different ways with having sounds being masked or not. And it seems to be more and more what we're finding is that this is a trait level difference or that we are identifying as we compare participants with tinnitus versus controls. So again, to reiterate, at the same time, we can detect and identify changes in large-scale neural networks in the brain using this resting state fMRI techniques and resting state functional connectivity techniques. And these are multiple networks. So this is the auditory processing, emotion processing, attention networks, the default mode networks. And more importantly, we're also now beginning to identify interactions among these networks, right? So that is also important in describing essentially the story of tinnitus. Okay, so some of these neural networks, I just wanted to provide a sense of where we are looking at. So this is sort of semi like a glass brain, and you can see that we put our seeds in these regions to detect any connections with the auditory cortex or the auditory network. These are the seeds we typically use for the default mode. So it's in the medial prefrontal as well as in the posterior cingulate. These are the seeds we typically use to identify connections of the dorsal attention network, so in the frontal eye fields and the posterior intraparietal sulcus. And these are the seeds we typically use when we want to identify functional connections of the limbic network. So limbic regions mediate emotion processing. So this should be emotion processing. So hippocampus and parahippocampus mediating memory, amygdala, emotion, insula is also emotion and also salience, and then prefrontal cortex. Lower sort of or orbital prefrontal cortex, again mediating emotion. So again, this is a very broad overview, and I'm trying to be with the Gen Z crowd and give you guys some memes. So when we started, before the emergence of brain imaging, what we had, so let's go back to year 2000, let's say, or 1990, we thought of the brain as it relates to tinnitus as a black box. We knew people complained of these noises, complained of the sounds they're hearing, but we did not essentially understand where it is in humans that things are getting affected. So we have made progress. This is going back about 11 years, and I actually have some work of Audrey Madu here as well. This was a review paper, and this was the very early days of resting state studies. And at that time, these were 6 studies. We found some commonalities, but we found some differences too, right? And now we've tried to work more on it. This is from our 2016 paper, where we are trying to also understand the connections between these regions and connections between networks, not just within a network, but across networks. And this explained a lot about severity of symptoms, right? For here, instance, we are very much worried about severe tinnitus versus mild tinnitus. And we see a difference with the amygdala. We see a difference in connectivity of the parahippocampal gyrus, and we think this is important. Then we have gone on further and tried to put this in the framework of loading in terms of cognitive resources, in terms of perceptual resources, and how does that affect how does that affect us doing, let's say, attention challenging tasks and so on. So this is where we are going forward. So very quickly, I'm going to be telling what is under the hood, so to speak, of our car here. And we continue to find this region called precuneus in many different studies, which shows reduced connectivity with the rest of the default mode. So precuneus is a region within the default mode network that is important when we are consciously aware of stimuli, consciously aware that we are hearing a sound, right? So one of the theories I have is that a lot of us will have tinnitus, almost all of us, but we just have suppressed being aware of it. And at some point, that suppression goes away, either after exposure to loud sounds or after some infection and so on. And the activity within our central auditory pathways perhaps rises up to the level of conscious awareness. So we see this connectivity, which is increased with dorsal attention network if you have more bothersome tinnitus or you have mild tinnitus. So the M here is mild and B here is bothersome. We also have done this large-scale study of multiple participants, 150 participants over two sides. We are finding some consensus about what does it mean to have tinnitus? What does it mean to not have tinnitus? And again, we see this connection with precuneus and intraparietal sulcus. And we also see there is replicability. So this is TFI, again, is a questionnaire. TPFQ is the tinnitus primary function questionnaire. And we see that there is consistency in how participants are reporting their symptoms, whether it's, they're high, more severe, or mild, and it's consistent across two visits. And we find that this consistency is reflected in the brain networks. So these are interclass correlation values of our seed regions that we're using to determine if they are the seed regions of different networks. And this is extremely consistent. We are finding for both the participants with tinnitus or their controls. What we also did a meta review of multiple experiments, not just from our labs. The previous one was just from our labs. And again, we are finding that parts of the default mode and some of the attention and memory are extremely, extremely important and very consistent about over these 26 experiments. So we're finding that this is very replicable, what we are finally seeing. So again, we saw more discrepant results, but we're also finding this consensus and consonant, essentially, results across these multiple studies, multiple labs over our heterogeneous population. So in the very last part of my talk today, I wanted to show that we are using this tool to understand when interventions are working and when they're not working. So this is a study using resting state, slightly different method, but PET, which is a positron emission tomography study. This was using hearing aids in collaboration with our colleagues in Sao Paulo, Brazil. And this is a very simple study. We have hearing loss controls without tinnitus. We have 19 tinnitus and hearing loss patients. Everybody was fed with hearing aids over a period of 6 months. We have pre and post, and these are some of the regions that seem to be implicated for tinnitus plus hearing loss compared to hearing loss alone. And I think that this kind of technique is important. And we have followed this up by looking at mindfulness-based cognitive therapy. Here you can see pre and post that there is a decline in symptoms. So this is questionnaire levels. So this is tinnitus primary function questionnaire. You can see a decline over the period of the intervention, which has persisted over the follow-up. And looking at the brain imaging, we saw some changes in gray matter, but what I'm showing here are changes in default mode network and connections with the auditory regions in thalamus and visual cortex. Again, this is follow-up versus pre-intervention with mindfulness-based cognitive therapy. And these are the regions that show the most change. And this is a connection between the default mode network with auditory areas and visual areas. We also see what has increased in terms of the functional coupling. And those were regions in the angular gyrus, which is sort of in the middle related to the parietal cortex. And so this is meant to convey to you how important brain imaging remains, how important it is to understand what is happening as individuals are showing these changes, improvement of symptoms due to intervention, right? We think this is a reliable tool, and I think that we are on the cusp of understanding even more and developing consensus in our field about tinnitus and its mechanisms. So the take-home message is that I hope I've conveyed to you that tinnitus is no longer considered to be peripheral. We think the source is in the central auditory pathways. We think it's not just one region that we need to worry about. We think it's due to several large-scale neural networks. We are taking a more global or holistic view, and I hope we as a field and we as in my lab are beginning to understand the neural correlates of severity, right? And how do they change with treatment? And I want to thank my lab and the our sponsors. We have a lot, but very much extremely grateful to our volunteers who come in for very little money and spend hours with us.